Good morning, ladies. Today we are looking at the first part of Faraday's law. So at this stage, you know that as soon as we take a magnet and a solenoid, and there's movement of the solenoid and the magnet relative to each other, a current is induced or a current is brought about in the solenoid. Now, let's take a look at Faraday's law. And Faraday's law looks like this. The magnitude of the induced EMF or voltage across the ends of a conductor is directly proportional to the rate of change in the magnetic flux linkage with the conductor. So Faraday's law is all about determining the magnitude of the voltage that is induced in the solenoid. This is what the formula looks like, but I don't want to look at the whole formula now. We'll do that in the next video. All I want to look at now is this part here where we say that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux. Rate of change, we all know, will be divided by time. But this magnetic flux is what I would like for us to look at. So firstly, we all know about the magnetic field strength, and the symbol for that is B. Now, you also just need to know that magnetic field strength is measured in Tesla. Now, what about magnetic flux? Magnetic flux, there's the symbol for it over there, is measured in Weber, and it is the number of magnetic field lines that pass through a given area perpendicular to it. So magnetic flux is all about the strength of the magnetic field and the area through which the magnetic field lines pass. So here I've got two examples for you. Here the area is circular, for example, and there's the magnetic field lines passing through that area. Here it's a square, and I've got magnetic field lines passing through that area. So how do I calculate magnetic flux? And this is what you can look at over here. Magnetic flux, which is measured in Weber, is equal to BA cos theta. B is the magnetic field strength, which is measured in Tesla, and A is the area through which these magnetic field lines pass. And this area must be in meters squared. Then cos theta, theta is the angle between your magnetic field and a normal to the cross-sectional area. And the best way to explain that is when we look at an example, which we'll do shortly. And then just over here, because flux is equal to BA cos theta, and flux is measured in Weber, we can also say that 1 Weber is the equivalent of 1 Tesla meter squared. So that just comes from the formula over there. Now let's take a look at an example. So the question looks like this. A square loop with an area of 2,4 meters squared is placed in a magnetic field of strength 0,8 Tesla. So immediately I can see that I've got area, it's already in meters squared, so I don't have to convert anything. The strength of the magnetic field, B, is given as 0,8 Tesla. And they say the field is parallel to the normal. So if you take a look at the diagram here, here's the normal in red that I've drawn in, because the normal is always perpendicular to the surface area. And here we can see the lines, the magnetic field lines, are parallel to the normal. And as soon as that happens, theta is going to be 0 degrees. And then they say determine the magnetic flux. So magnetic flux is what I want to work out. And as we've already said, magnetic flux is equal to BA cos theta. B is magnetic field strength given as 0,8. A is the area given as 2,4, cos 0 degrees, and the answer that I get is 1,92 Weber. Then the second example, a square loop with sides of length 2 meters is placed in a magnetic field. So what have they done here? They haven't given us the area. They have given us the side, but they do say that it's a square. So yeah, I have to go calculate the area, which is going to be length times breadth, which is 2 times 2, and I get 4 meters squared as my area. Placed in a magnetic field of strength 0,3 Tesla. So I have got B as 0,3 Tesla. If the field makes an angle of 50 degrees with the normal. So take a look over here. Here's the area. Here are the magnetic field lines. There's the normal, which is perpendicular to the surface area, and the angle between the normal and the field line is given as 50. So theta is going to be 50 degrees, and we want to calculate the magnetic flux. So once again, BA, the theta is equal to, flux, is equal to BA cos theta, 0,3 times the area 4 times cos 50, and 0,77 Weber is the answer. Then the last example that I would like to look at is the worked example that you've got in your textbook on page 202. So now the strength of the magnetic field is given as 0,02 Tesla. The angle between the magnetic field lines and the normal, which is perpendicular to the surface area, is 45 degrees. The radius of the circle is given as 20 centimeters, and we know that we need area. So first thing we do is we take the centimeters and we convert that to meters. So 20 divided by 100 gives us 0,2. And then the area of a circle is pi r squared. So pi 0,2 squared, and the area we get 0,125 meters squared. And magnetic flux is what I want to calculate. So once again, magnetic flux is equal to BA cos theta, 0,02 times the area that I calculated, 0,125, times cos 45 degrees, and 1,77 times 10 to the power of negative 3 Weber is the answer. You don't have to write the answer in scientific notation. So if it's 0,00, then that's perfectly fine. And then what you can do is look at exercise 10.1, which you'll find on page 202. And if you can please then do that for next time, just to practice some of these questions. Thank you, ladies.